Thank you very much, Robert. It's a very interesting event. So my name is Florian, and I'm working as a CTO focused on automotive and AI use cases at Dell Technologies. I am part of the Unstructured Data Solutions business unit, and today I will talk about the ideal infrastructure for ADAS and AD workloads. So if I'm talking about ADAS, I'm referring to advanced driver assistance systems. It is similar to a traffic sign recognition system or a lane keeping assist. And if I'm talking about AD, I'm talking about autonomous driving. So everything that relates to self-driving cars. So let me quickly introduce myself. As mentioned already, my name is Florian. I'm part of the global CTO office focused on our products of the Unstructured Data Solutions division. This is mainly storage. And I've joined Dell around about 1 year ago, 1.5 years ago, and I was working in the automotive industry, responsible as a technical director for the development of ADAS and AD functionalities, everything that has something to do with computer vision and machine learning, data management and tooling. And during the last couple of years, I was working for a Japanese company, Panasonic Automotive. And I'm based in Lindau in Germany, near to the Bodensee. It's a wonderful region. And I was doing my PhD in the area of machine learning and artificial intelligence. So today I will talk about the typical development workflow of ADAS and AD systems, and also test data retention and synthetic scenario generation. I will share some typical ADAS and AD facts. So how much storage is needed, how much CPUs are consumed by companies focused on developing self-driving cars. And then I will highlight 3 use cases that I see very important in setting up an infrastructure for ADAS and AD. The first use case is how to implement or develop a hybrid cloud architecture for AD and ADAS use cases. In this example, hardware in the loop. I will talk about a new white paper that we've released last Friday, focused on deep learning and artificial intelligence. For the development of self-driving cars, I will speak a little bit about real-time streaming, and then I will conclude this talk. So I will speak around about 15 to 20 minutes, and feel free to interrupt me if you have questions, or type in a question in the Q&A chat, and I will answer this after this presentation or in between. So what I'm seeing right now in the ADAS and AD industry is that companies are adding the vehicle as a crucial part into the development lifecycle of ADAS and AD systems. So I've divided this process in four tasks. And the first task is to focus on an in-car compute and storage system. Some typical tasks running inside of the vehicle are, for example, data collection, context labeling, pre-labeling, and over-the-air updates, or how to stream data generated by the vehicle on the field through 4G or 5G into the data center. And this is prominently used in the development of ADAS and AD systems. So you would need hardware like GPUs, CPUs, in-car storage systems to collect the data and to train your algorithms, and also to enable your developers to push out updates from your algorithms over the air into the infrastructure. A prominent example is Tesla. So Tesla releases frequently new functionalities for the drivers, and the drivers are collecting new data to allow Tesla to improve these functionalities. The second box after you've collected this data is that you have to offload the data that was generated on the field into a so-called ingest station or into a satellite. And some tasks running in these satellites are labeling. So for example, you have to outsource your data to an external agency to allow them to create bounding boxes to label pedestrians and road lane markings and everything that is on the street to train the algorithm. And some additional scenarios or tasks are focused on edge case scenario identification, data cleaning, or data compression. And all these satellites that we have located in different countries, more on the following slides, are connected to a centralized data lake. And this centralized data lake is typically located at the headquarter of the company. So if we have a German customer out of Munich, the centralized data lake is of course located in Munich, and different satellites located in any other country, these ingest stations are connected to this centralized data lake. And then the developers connected to this centralized data lake are able to start and stop computer vision algorithms, the training process of deep learning algorithms. They are also able to locate sensor file to focus on data management, and they can connect their own applications through APIs to the centralized data lake. For example, a typical use case is that your algorithm is not able to detect vehicles on a German highway under 120 kilometers per hour. The developers could locate all test cases and scenarios to cover the missing parts or the missing training examples to improve the algorithm. What I'm typically seeing for a small ADAS project is that you have around about 850 concurrent in and out threads that are reading and writing data. A lot of different applications such as software in the loop processes, hardware in the loop processes. And if we assume to have 10 small projects, you will easily end up 8,000 of different threads connecting to this centralized data lake. So what are the key challenges in setting up these infrastructures focused on deep learning and artificial intelligence for the development of AD and ADAS use cases? So typically we have to deal with complex test and validation processes. Cars must operate safely on the streets, and we need a fully automated tool chain from collecting data on the field through ingesting the data into the data lake and infrastructure to the test and validation and homologation of ADAS and AD functionalities. The second challenge is, especially in the automotive industry, we are working in multi-site and multi-party projects. So a company like a big OEM has its own suppliers. They are called tier ones like Continental and Bosch, and these companies also have their own suppliers that are delivering pieces to the tier one and to the OEM. And very often we are working in multi-site projects. So we have a development team located in Germany, another one in Japan, another one in China, in US, in Spain, everywhere in the world. So we have to enable developers to locate and access the data, and also to enable them to train machine learning algorithms in a distributed way. The next challenge is if we are focusing on AI and machine learning algorithms, this is an iterative process. So we are training our algorithms, we are testing our algorithms, we are retraining our algorithms, and we are improving the code, etc. So you have to integrate everything in a fully closed development chain. And then the last point is focused on data growth. So if you deploy a small ADAS and AD project, you will need petabytes of data. If we focus on current developments, you will end up around about 200 petabytes of data that you will need to develop a vehicle focused on SAE level 3. Why do we need so much data? Because we need a lot of kilometers and miles that we have to use to test and validate our system. And as you know, there are plenty of different conditions out there in the real world, different weather conditions, road conditions, different incidents that could happen. And we have to cover data or collect data in multiple geographies, different countries under different weather conditions, road conditions. And in the automotive industry, we have a lot of different applications and test and validation processes. Just to name a few, companies are focused on hardware in the loop testing, software in the loop testing, model in the loop testing, vehicle in the loop testing, driver in the loop testing. We have to cover the legal validation of these algorithms. And we have to also focus on synthetically generating these scenarios, because very often it is too dangerous to collect an incident or a scenario in the real world. Take a look to this bicycle accident that you can see right now on the screen. How to train your algorithm to take care of scenarios like this. So companies are focused on generating scenes and edge cases synthetically. So on the right side, you see some famous scenarios generated by an open source framework called Kala. And these synthetic scenarios are created by using techniques out of the gaming industry to precisely generate specific scenarios, or to create the full spectrum of possible scenarios, or also to create test cases that are too dangerous to produce in the real world. Or you can use synthetic generations to create variations of the same use case. So you are driving at 120 kilometers per hour on a German highway, and now you want to have sunny conditions, then you want to have rainy conditions or icy conditions. And this is exactly a key area on that a lot of companies are focused right now, also to save costs, of course. So let me share some typical facts of companies that I'm working with. So big companies focused on implementing or developing self-driving cars, they are collecting 5 petabytes of data per week. 1 petabyte are 1,000 terabyte. They have 40 petabyte of active training and test data sets. As you know, we have typically up to 30 different sensors in the vehicle, and companies are sending out 100 and more vehicles to the field everywhere in the world to record the data under different weather conditions, illumination conditions. And we have 2,500 labelers connected to this centralized infrastructure to label data, to annotate bounding boxes. So for example, this is a cat, this is a traffic light, this is a dog, this is a road lane marking, the sun is shining, whatever. And a typical project consists of around about 1,000 developers. So if you check out some prominent startups out of the ADAS and AD industry, these companies would have around about 1,000 developers working continuously to develop self-driving cars. So how to create an efficient infrastructure? So what we have initially is a centralized data lake. And as mentioned before, this centralized data lake is located typically at the headquarters of these companies. And then we have different satellites connected to this centralized data lake through a data management system. So one of the remote sites could be located in China. But of course, in China, we have to make sure to not violate against the Chinese regulations around data sharing. So you are, for example, not allowed to move or copy any data out of China before it got proven by a mapping provider. So you have to make sure to follow these restrictions. And another remote site could be located in US, for example. And if you have to move over data from US to Germany or to Europe or to Japan, of course, you have to make sure to move over this data in a cost-efficient way, virtually or physically. And the bandwidth and latency is very often not that great because of the distance. Another data lake could be located in north of Germany, and this remote site acts as an ingest point, and developers could log in through the data management system to locate the data. And then typically we have the long-term backup and archive, and the whole data lake is connected to the public cloud. So what is a typical development life cycle in each of these satellites look like. So as mentioned before, we are sending out vehicles to the field to record data with different sensors, camera, radar, LiDAR, GPS, etc. Then the sensor data gets ingested through a disk load station in one of these remote sites to the centralized data lake. And then we are starting a lot of processes, as I've mentioned before, the data labeling process, the process around test and validation, to test and validate vehicles operating on German highways, on Spanish highways, everywhere in the world. And then we are starting the deep learning environment to train the algorithms. And we are also starting the hardware in the loop and software in the loop test farms to test the real physical hardware and to measure KPIs from algorithms, like how many vehicles are detected, to measure the quality of the algorithm. And then, of course, as mentioned before, we have the backup and long-term archive located, connected to the centralized data lake. So I've on one of the slides, I've mentioned the public cloud. So in general, there are two types of customers or two types of companies. And hardware in the loop is a process of physically ingesting data into the real hardware, because you have to test and validate your real hardware. And this is very often, or it is not possible to work on if the data is located in the public cloud, because of latency issues and bandwidth issues. And you have to focus on connecting your physical hardware directly to your storage located in your on-premise data center or in a co-location. And I've mentioned these two types of customers. The first type of customer is a customer that has a lot of data in the public cloud, and the customer needs to test and validate the data by moving data out of the public cloud into the physical hardware. The second customer is a customer that has a lot of physical devices located in the headquarter, and this data must be moved over into the public cloud to utilize 30,000 CPU cores, for example. So some reference architectures and use cases are showing this solution to move data into the public cloud to physically test these ECUs. And another use case is to move data out of the public cloud into the physical hardware. So hardware in the loop testing by using the public cloud is provided in both directions, into the public cloud and out of the public cloud. I've talked about another use case around deep learning on ADAS and AD data sets. So there are a lot of different data sets available on the market, open source data sets created by leading universities or by big companies that wants to offer these data sets to other companies and research organizations to help to move the development of algorithms forward. And there are millions of different images, annotated images generated by LiDAR sensors, radar sensors, cameras, and HD maps available. And we've evaluated a prominently used data set on our infrastructure. It is called the Cityscapes data set. And we've measured how much time do we need to compute a deep learning network, in this example, a so-called single shot detector that is focused on object detection, by using 64 different GPUs. And we've demonstrated that we've been able to reach 4 minutes for a full training process of these deep learning networks. And we've also shown to scale linearly from 4 to 64 GPUs by utilizing the GPUs up to 96% in average. From my perspective, this is a great value on real automotive or ADAS and AD focused data sets. So Robert, do we share these presentations after the presentation with the audience?
Yes, we do.
Okay, perfect.
So if you allow us, then
yeah, of course. Yes. Okay, thank you. So I've added a link, and you could click on this white paper that we've published on Friday afternoon. So you could check the full report of these benchmarks. So the third use case and the last use case is focused on real-time streaming. So I will not go into the details, but you can reach out if you want to have more information on this use case, but let me show you a typical real-life example. So vehicles are located on the field to collect sensor data. And this sensor data gets sent over through 5G to a so-called ingestion engine. So you are able to send over images and telemetry information directly to the data center. Remember the use case from the Tesla. And this data gets analyzed by your development teams to build a deep learning model to improve this functionality running in the vehicle. And the idea is, or the concept is, that this data is ingested automatically into your infrastructure and you can process the data in real time. So for example, you could detect some events. If your autonomous emergency braking system got triggered because of a false positive, you could analyze this event and you could collect the data that caused this false positive to update your deep learning model over the air inside of the vehicle. And this is so-called a streaming data platform. Collecting data, ingesting data, analyzing data, and send information back to the vehicle or to any other sensor or use case focused on smart factories or digital cities. So that's it from my side. What is Dell doing in the automotive landscape? We are supporting our customers by educating them around automotive workloads. We're doing workshops, and we are offering, of course, compute, network, and data management systems. And we are setting up these hybrid cloud environments to connect the data centers seamlessly to the public cloud. So that's it from my side. Thank you very much. And I'm handing back to Robert.